Okay, thanks very much to the organizers for inviting me. My understanding is that, so I don't know too much about this community. I'm new to this group, but my understanding is you're interested in getting more into uncertainty quantification. And that's why I'm here, is to talk some about some tools that are being developed within the Department of Energy for optimization and uncertainty quantification. So my name's Mike Eldred. I'm in the Optimization and Uncertainty Quantification Department at Sandia in Albuquerque. Okay. So what is DAKOTA? DAKOTA is a software toolkit. Well, let me first give you a brief outline of what I want to talk about. I want to talk some kind of pragmatically about what DAKOTA is and how you might use DAKOTA. And then, as time permits in the latter part of the talk, I'll highlight some uncertainty quantification algorithm capabilities that you may be interested in using for these sets of applications. So what is DAKOTA? DAKOTA is a framework for iterative analysis. Okay? So take your simulation framework and use it as a function evaluator to repeatedly map some set of model parameters into some set of quantities of interest. Okay? Pretty simple and straightforward. We're just going to map inputs to outputs and then close the loop and iterate to do things like design optimization, uncertainty quantification from ensembles, calibrating models using, say, nonlinear least squares, or performing global sensitivity analysis. 2 talks ago, the speakers talked a little bit about sensitivity analysis, and so that's very closely related to uncertainty quantification. So DAKOTA is an object-oriented toolkit. We began it in 1994, so it's been around a while. It's coming up on its 20-year anniversary. But it's grown. It's still not a very large team. We're only about 10 folks at Sandia, Albuquerque, and Livermore. We also leverage a number of developers of this is third-party libraries, so a number of capabilities that we pull into the framework developed, say, outside of Sandia. We do a variety of releases, we do training sessions, we do mini tutorials, we've got a variety of outreach activities. Perhaps the most important thing on this list, as was alluded to earlier, is we're an open source software framework. So you can freely download both source distributions and binary distributions, and we support Linux, Mac, and to a lesser degree Windows, but that is becoming more important as we go forward. And we do have some community mechanisms to interact for support. If you're interested in looking in more detail, dakota.sandia.gov has got a variety of materials, including some getting started information, a couple of manuals, and then also we've posted our training materials for when we do trainings. So that's a great place to get started. Okay. Now a little bit more detail on what the framework looks like. It's object-oriented in C++, so we have the notion of class hierarchies that give us an abstract behavior at the top level, and then we specialize it as needed to do specific algorithmic things. One of our main hierarchies is this iterator hierarchy, and hung off of this abstract class, you see design of experiments, uncertainty quantification, design optimization using gradient and non-gradient methods, simple parametric analysis, just interrogate how your model quantities of interest vary as you vary the parameters, as well as calibration tools, for example, tuning your model parameters to match your experimental data. It seems that you have good sets of experimental data becoming available. Okay, so that's our iterator. Our iterator iterates on a computational model, which contains basically a set of inputs that are mapped into a set of outputs through the use of an interface. And then the inputs can be a variety of things, depending on whether you're doing design or whether you're doing uncertainty quantification over random variables. And then on the output, we have the notion of an abstract set of quantities of interest and their first and second derivatives, mapping between them. And you can either use a simulation-based mapping, such as a PDE-based sediment modeling system, or you can insert alongside it or replace it with a variety of different approximations. So data fits, multifidelity approximations, reduced order models, a variety of things that you can use as surrogates if the real simulation is too expensive to use in, say, some context of, I don't know, global optimization, for example. Okay, so that's our iterators and our models. These things actually provide foundational components that allow us to put things together into what we call a solution strategy, so we can do more sophisticated things using these pieces. A good example of that is that if you wanted to do, say, design a system in the presence of uncertainty, then you can take your design optimizers, your uncertainty quantification, maybe put in some surrogate models to reduce expense, put these things together and construct a multi-component type of solution approach. Okay? So final comment here is an important one for the slides going forward, is we have 6 components here, and this is what we'll use to specify what we want DAKOTA to do. We have an iterator or a method, a model, parameters, interface responses, and a strategy. And those 6 pieces define an input. Okay? We largely grew out of the NNSA side, the defense side of the Department of Energy, but we're also, within the last, I'd say, 4 or 5 years, getting much more actively involved in Office of Science applications, the other side of the DOE. And that includes things like wind energy, working on a variety of wind turbine configurations, collaboration with, to some degree, with NREL down the road here. Also working on nuclear power. This is the CASTLE project. This is an energy innovation hub. CASTLE stands for Consortium for Advanced Simulation of Light Water Reactors. This one is climate modeling, as you can see here. This is climate science for a sustainable energy future using the community atmospheric model here. And then within the last year and a half, we're part of the QUEST Institute within the SIDEC program. QUEST is Quantification of Uncertainty in Extreme Scale Simulations. So all of these have in common high fidelity modeling and simulation and the need to do uncertainty quantification. And in many cases, say in this case of these climate models, a good example, we may only be able to afford to do a handful of simulations, on an order of 5 or 10 or something like that. I guess that's 2 handfuls. But not very many simulations, and we may have a large number of random variables. So that provides some real challenges if you're going to do uncertainty quantification using some kind of ensemble-based approach. Okay, so that's kind of the high-level description of what DAKOTA is and some of the things it's connected to. Now let me dive a little deeper in how DAKOTA works. And there are a couple different ways that you can use DAKOTA. This is the simplest. Okay, this is using a command line driven syntax with files, and we're going to communicate with the simulation in a completely black box manner using the file system. Okay, so what that looks like is you would define your DAKOTA input file that selects one of these types of studies in the DAKOTA executable, and it's going to communicate with a separate, say, settlement modeling simulation through the file system. So there's going to be 2 separate executables. DAKOTA is going to spawn instances of the simulation and going to communicate with it through the file system. And the way that might look, what that might look like is DAKOTA would spawn a parameters file. It contains the data, the random variables, the design variables, whatever the inputs are. Okay, and then it's going to invoke some kind of driver to run your simulation. Now this could be the simulation itself. If the simulation itself is modified to read DAKOTA input and write DAKOTA output, that's not usually the case. So usually we have some kind of thin driver that's going to accomplish the mapping from inputs to outputs. Okay, so here sits your simulation. It takes its own inputs and outputs. We need to do some pre-processing to take this data and insert it into the code input. We then take the code output and we do some post-processing and extract out our quantities of interest to close the loop. Okay, pretty straightforward. This is known as just wrapping your simulation. That's the simplest approach. And then we do this some number of times, we iterate, and we report the per iteration output and then some final summary of the optimal solution or the final statistics, etc. Okay, so that's the simple case, just black box communicating through the file system. We can get a little fancier than that, but before I describe that, let me show you an actual input file. So in this kind of command line driven syntax with an input file for DAKOTA, this is a sample. We have a strategy, a method, a model, variables, interfaces, and responses, those 6 pieces that I described earlier. The first 2 are setting up the type of study that's going to be done. In this case, just a simple parameter study along a vector, okay, starting with some number of steps and a step vector. And then this part from model, variables, interface, responses defines how how you're going to map inputs to outputs using the simulation. Okay, in this case, I have a couple design variables, I have a couple state variables, they have an initial point and descriptors, I have 3 quantities of interest that I care about: area, stress, and displacement, and I'm not computing any derivatives. Okay, and then mapping in between the two, I could be using a system call or a fork. In this case, I'm just using a direct interface to a test simulator that's already linked into the DAKOTA executable. Okay. So that's what an input file looks like, and many people who use DAKOTA use it in this simple mode, and they just edit and update input files as needed for particular studies. I would point out that it's really pretty straightforward in this model to go from simple parameter study to a sensitivity analysis to a UQ to a design under uncertainty. It doesn't require a whole lot of changes. This stuff may stay pretty much the same, and it's just a matter of flipping some selections in the method specification. Okay, so by design, it's intended to be able to do very different types of studies pretty easily. Okay. But if that's not your thing, if you would like a more turnkey type of approach, and many folks, particularly on more of a Windows environment, would like to see more of a GUI-based interface, we can do that too. We have a tool called JAGUAR that provides a user interface. This may be a little hard to see, but this is kind of 3 different views of setting up a problem. The first view here is everything that's available in the input specification you can manage. From multiple specifications of models and multiple methods, DAKOTA in all its gory detail, and this is really intended for more kind of expert users. You can also view an input deck in the same way that you might do with Emacs or VI, but inside the GUI you have some additional niceties like syntax completion and tooltips and some other kind of usability features that make it easier to deal with the DAKOTA syntax. And finally, the simplest case is when we set up what we call a wizard. It'll lead a new user through the process of setting up a particular, say, sensitivity analysis or UQ type of study. So we have those tools available as well with the intent of making it simpler for new users to access the tools. And the final case is a more advanced case, but one that's potentially of interest to this community. If you guys are in the business of developing kind of integrated modeling and simulation frameworks, as I think I'm hearing is the case, then you may be interested in embedding these algorithms as a service within this larger framework. Okay? You can do that as well. We have a number of codes, both internal to Sandia and external, that have been doing this. The big advantage, as you might guess, is that you can unify the input and output syntax. You can eliminate some of this business. You don't need to do this anymore. You don't need to do this anymore. You can communicate directly through parameter lists, eliminate some overhead in setting up the problem, and really make the thing nicely unified, nicely integrated. Okay? It also has some nice features in terms of parallel execution. If you're one executable instead of 2 executables, that simplifies things on the parallel computers, things like this. So I'm not sure what the level of interest is in this, but if you are interested in this, we have documentation for embedding DAKOTA as a library, and we're happy to help. Final note here is that this idea of linking the 2 capabilities together is intrusive in software, but not necessarily intrusive to the algorithms. But you can consider being intrusive to the algorithms as well. And shown here on the right is we're developing this within, say, the DAKOTA framework, where we have a fully non-intrusive approach from the algorithm, where the simulator is untouched. The only difference is now we're communicating in a little bit more efficient way. Or we could go to where we have an approach that's intrusive to the coupling between multiple physics, but the individual physics components are left alone. And you can go fully intrusive to the physics, where you're actually having the optimizer or the UQ method invade into how the simulation is performed. An example of that for optimization is something called simultaneous analysis and design, or SAND. In the case of UQ, stochastic Galerkin methods are intrusive to the physics. Okay? So depending on how fancy you want to get, you can just go software intrusive, or you can go algorithmically intrusive at a couple different levels. Okay, final slide in this part of the talk is on parallel computing. So DAKOTA was originally funded by the ASC program from the NNSA, which put a lot of emphasis on large-scale parallel computing. So early in our existence, we were doing fancy things like this on ASCII Red and subsequent platforms, ASCII White, Red Storm. where the basic idea is that there's lots of concurrency to be exploited in these types of studies. You may have, you might be dealing with mixed aleatory and epistemic uncertainties, mixed continuous and discrete design variables. You might have surrogates involved. You might have multiphysics involved. There are lots of different pieces that go into performing a single simulation and doing this type of iteration. And so there's what we've developed is what we call a multi-level parallel computing capability. So the basic idea is perhaps best described here, where you have some initial block of processors, might be MPI-COM world, and you're going to partition that into concurrent blocks of, say, iteration. Maybe there are concurrent optimizations within a branch and bound, for example. Each of those you take each one of those blocks, and now you further subdivide it into concurrent data requests for that optimizer. Each data request might involve multiple components that can be decoupled and performed concurrently, each one of those executing on multiple processors. So you can do this any number of levels. The basic need is that you need to do this recursive partitioning and nested scheduling. Okay? And you need to do that nested scheduling in a smart way such that some idleness at some lower level doesn't kill the overall efficiency of the process. You need to understand what's going on each one of those levels and schedule in a multi-level sense. Okay? So that's the most advanced case, but we also support these other cases. If you just want to run DAKOTA serially and have it fire jobs at a queue and let the queue take care of it, we can do that. Or if you want to distribute work using over a network of workstations or a cluster of SMPs, we have modes for that as well. So there's a lot of parallel computing capability to draw on for doing concurrency, for exploiting concurrency in these simulations. Okay. So with the time I have remaining, I thought I'd talk a little bit about UQ. So as I've mentioned, we have these optimization capabilities. We have nonlinear least squares capabilities. We have global sensitivity analysis. We have uncertainty quantification. I'm going to highlight the uncertainty quantification. And this is a tabular view of all the different algorithms for UQ in DAKOTA. I don't know how familiar you are with different UQ approaches, but the comment that I'd like to make at a high level is that UQ in many communities is kind of dominated by either random sampling, okay, probably everybody's heard of Monte Carlo samplings, many of you probably heard of Latin hypercube, or on the other extreme, local gradient-based methods for doing UQ. There's what's called mean value method, which is very inexpensive, very scalable, but also very approximate. And some of you may have heard of first order and second order reliability methods, FORM and SORM. These are probably the most popular techniques in the community. Unfortunately, they're all kind of at opposite ends of the extreme in terms of robustness and efficiency. Okay? In one case, you have robustness, but you don't have efficiency. You have slow convergence. In the other case, you have efficiency, but it's very approximate and not very robust. In fact, it can give you very bad answers if the system is even mildly nonlinear. So some of our research has been focusing on global methods that eliminate the issues with local gradient methods, but have much more advantageous convergence behavior relative to the 1 over square root of n type convergence you get with Latin hypercube. Okay? So at risk of losing you, I'm just going to show you briefly what some of that looks like. So you get just a basic flavor, but I'll try and do it at a very high level. Okay? Okay. So in our defense programs and in our Office of Science applications that I showed, again, we're kind of faced with this challenge. We've got severe simulation budget constraints. We can't afford to do 100,000 simulations. We can afford to do more like 5 or 10, maybe 100 if we're lucky in terms of simulations. We're also faced with moderate to high dimensionality and random variables, which I define as tens to hundreds of random variables. So if you have, order 10 random variables and you're only able to do 30 function evaluations, that's a very coarse interrogation of that random space, okay? We're often in that situation, unfortunately. That situation can be compounded with a number of other factors, like we have mixed types of uncertainties, which we want to segregate the effect of those uncertainties and do some type of nested iteration. That compounds the expense. We need to evaluate probability of rare events, or we need to look out in the tails. That compounds things. And finally, if the response function is non-smooth, there isn't nice smoothness that can be exploited in a fast converging method, then that's also going to be an impediment. So we've been investing in a variety of research activities to try and address these common challenges that, again, exist both on the defense side and the Office of Science side. And I'll summarize them as basically, we're forming global surrogate models, but if we can be adaptive, then we can reduce the effective dimensionality. We can refine in the stochastic space only where interesting things are happening, where things get very nonlinear, where things get non-smooth. Where things are smooth and low order, we don't need to spend a lot of effort there. If you can develop adjoints, okay, if you guys can give me derivatives, you only have, say, a handful of quantity of interest, but you have a 100-dimensional problem, but you can give me adjoints, then I can use those to good advantage. There are a variety of ways. And inform my global approximations with a lot of local derivative information and really address scalability with that. And finally, if I can detect sparsity. If you have only certain terms in your input to output mapping that are really important, and I can sense those using a coarse sampling in a way that I'll describe here in just a moment, then that can be an effective technique for mitigating these challenges. Okay, so these are themes within kind of a foundational investment in UQ. And then once we've done that, I probably won't have time, but there's also work in leveraging that in terms of higher level studies. Okay. So here's an introduction to a class of uncertainty quantification methods. Who's heard of polynomial chaos? Okay, not many, 2 or 3. Okay. Well, so these methods, there's a method called polynomial chaos and there's a method called stochastic collocation. They're very closely related. In both cases, what we're trying to do is just capture the functional relationship between a set of random variables xc and some quantity of interest r using a series expansion. Okay. In this case, in the case of polynomial chaos, despite the intimidating name, we're just using a set of polynomials here that are orthogonal to the weight, to the density function of the random variable. So we know the basis, we select the basis, and we need to compute the coefficients that reproduce the input to the output mapping. Okay, that's it. 2 minutes. Closely related is stochastic collocation, where now we know the coefficients, the response values at the sample points, and we need to form interpolants to reproduce the input to output mapping. The very nice thing about either of these methods is that you can get behavior that looks like this. Maybe a little hard to see, but what I'm plotting is the residual in a cumulative distribution function, one of the sets of statistics we really care about, versus number of simulations on a log-log scale. This is what you get from LHS. You get a 1 over square root of n, a slow algebraic convergence rate. Okay? Whereas with these spectral methods, you get a spectral type convergence. You get a super algebraic. Under certain conditions, you can get an exponential convergence rate. Why do you care about that? Well, if I wanted my CDF accurate to 10 to the minus 2, I'm going to require greater than 100,000 LHS samples to get there. Whereas with a fast converging spectral method, it's more like 20 or 30. Okay, so the savings can be significant if there's some features in the problem, in particular smoothness, that can be exploited. Finally, there's a lot of flexibility to tailor the forms, what terms you keep in these expansions to do basically P refinement or H refinement, very analogous to deterministic finite element methods. Okay, so let me just real briefly go through these because I'm running out of time. You can form these things on unstructured or structured grids through a variety of ways. If your simulation's prone to failure, you might want to use an unstructured grid and a regression-based approach because you can be fault tolerant that way. Okay. If you have a situation where things could be potentially very anisotropic, meaning that some random dimensions are more important than others, then you want to do something like adaptive refinement. Okay? You want a method that can figure out, for example, that it needs to refine more in this dimension and less in this dimension. Okay? And we have methods for that. Okay? Again, we can use adjoints. There's ways to use adjoints in a polynomial chaos regression approach. We can also use them within compressed sensing. We can use them within gradient enhanced interpolation by using basis functions that, for example, reproduce the value. These type 1 basis functions that reproduce values with 0 derivatives, or type 2 basis functions that reproduce derivatives with 0 values. You can get adjoints in your simulation. We can put them to good use. And finally, if you have a problem that looks like this, if you have discontinuities and non-smoothness and challenges in the variation of your quantities of interest, we have techniques to reformulate the problem in terms of what's called the hierarchical surplus, do local error estimation, and do local refinement. For example, as shown here, local refinement around the discontinuity. Okay. And the final thing that I'll probably get to here is compressed sensing. So this is a very promising technique if you're in that situation that I mentioned, that you have a relatively high dimensional space, you can only afford to do a few simulations, and maybe your goal is just to get what are the dominant effects in the uncertainty. Okay, what are the 5 terms that drive the variance the most, for example? So here's a regression approach for solving for those chaos coefficients that I showed you earlier. If you underdetermine the system, then the traditional approach to select among the infinite number of solutions to the underdetermined problem is to pick the one with minimum L2 norm. Alternatively, you can seek a sparse solution. You can enforce a regularization that tries to minimize the number of terms and identify just what are the most important terms in that expansion. So shown here, and we have a number of algorithms for doing that, which I won't go through, but this is basically showing a comparison between the traditional SVD approach that's here, the minimum L2 solution, versus a compressed sensing, which seeks sparsity. Okay? So if you have a problem with sparsity, I'm getting good results here using 10% of the data that's needed to fully determine the system. So these types of techniques can be very effective in that kind of sparse regime. Okay. I wanted to talk about building on that foundation. There are methods, multifidelity methods. Okay, and the basic idea here, just to get the basic idea across, is that you're going to break the problem into parts. You're going to approximate separately the low fidelity model and then some term that's the model discrepancy. And so the idea here is that this guy's cheap to evaluate. I can do lots of them. If it has useful trends, then I can piggyback it and resolve a discrepancy that's hopefully less difficult, is less complex, is more sparse than the original high fidelity problem. So I can leverage the foundational things I just talked about with also low fidelity models and combine adaptive sparse grids and compressed sensing and do some cool stuff in a multi-fidelity setting. Okay, and we're doing these types of things with Office of Science applications. This is a vert-axis wind turbine. In this case, we've got, NREL has some nice design codes that run in a few seconds on a single processor. But we'd really like to be able to predict things like dynamic stall in these turbines using LES, large eddy simulation. So many orders of magnitude. This is executing for hours on hundreds of cores versus seconds on a single core. So we can afford to do a lot of these and then use those to inform the uncertainty quantification problem for the high fidelity model. Okay, last slide. Again, the first part of the talk, I hope I showed you that DAKOTA provides a variety of different types of iterative algorithms for doing optimization, calibration, sensitivity analysis, and uncertainty quantification. We've put a particular emphasis on parallel computing. We also, as you evolve in your capability with DAKOTA, you can move to more sophisticated things that involve multiple iterators, surrogates, nesting and recasting. And if you're just getting started, we also have some capabilities that are targeting the idea of lowering the bar, right, for adopting some of these methods. And then I talked about some of the challenges that we're faced in the UQ and what some of our investments are, both at a foundational level and building on that foundation. So thanks.
Yeah, thank you, Michael. Any questions?
Hi, thanks. I think DAKOTA is so nice because it allows people to compare different things, and that helps mature all this scientific stuff. I did just want to say one thing. I think there's been recent work suggesting that local methods are a lot more useful than is sometimes indicated. And actually, some of that's being presented in a clinic at 11. So I thought...
Local uncertainty quantification methods?
Yeah.
Like form type methods? Or?
Yes.
Okay.
Yeah, yeah. So
if you understand your problem and know that you don't have a lot of non-smoothness or multiple modes of response, then they can be very effective techniques, absolutely. The civil engineering community, for example, uses them extensively. Right. Because they know the character of their response. So if you have that kind of special knowledge, I'm not at all against using those methods. They can be very effective. But for a general method where you maybe don't know what to expect, they can be, in that context, a little dangerous.
Yeah, so we're suggesting...
It can badly mislead you.
Right. Sorry.
You go ahead.
Yeah, so we're suggesting a multi-location local method where you actually evaluate it in a number of different places so you can address that issue fairly well with fairly few runs. I mean, it's
Great.
it's kind of better than we thought it would be so far with what we've done. So thanks.
Yeah, I'm interested to see that. Thanks.
Hi, thanks for the nice talk. I was wondering, what about the compatibility? If I want to use this in dynamic cases, like I want to use this somewhere in between the iterative process, if I'm using a different software platform, how compatible is it with your? I mean, you're talking about writing .exe files. You send in an input and get an output. A single print statement is very costly, right? Did I probably miss that, or?
I'm not sure I'm following you completely, but let me go back to this. This guy. I think this is what you're talking about. You're saying that
yes,
the file I/O might be expensive in certain situations, or you might be wanting to run this executable a different place than that executable. Is that
true? That's what I'm talking about. If my code is in a different platform than yours, C++. Yours is in C++, right?
Yeah.
So if I'm writing my code in some other language, and I want to use your uncertainty thing dynamically in between an iterative process, like I'm.
Okay. I think I understand the question. Yeah. So there's a couple things you can do. So really the only requirement here is that I have something that's executable. It doesn't have to be in C++ by any stretch of the imagination, because I'm not linking in this example. I'm not linking anything together. I'm just creating, say, a system call that's got to execute a process. Okay. So if you can automate your simulation in some way and have some sequence of calls that automate the process of running through here, then we can drive that. And I don't care if it's a script, I don't care if it's an executable file, I don't care what language it's written in. That's the general answer, is that it's really agnostic to how this guy was implemented and how this wrapper was implemented as well. It just has to be an executable program on the system or on some other system. Now, if it happens to be a scripting language like MATLAB or Python, we have some special interfaces to that, because if you just kind of naively put MATLAB here and bring it up and down, you spend a lot of time, there's a lot of overhead just bringing MATLAB up, right? And then closing it down. So we can do something where we instantiate an instance of the MATLAB engine or a Python engine and bring it up once and then fire work at it, okay? And then when we're done, then we close it down. So I'm reading between the lines that maybe that's what you were thinking of?
Yeah, it's exactly what I asked. Yeah, thank you.
Okay.
Hi. Thank you for the talk. Sounds very interesting, very sophisticated. I have lots of questions, but the real question, I guess, is suppose I can give you adjoints, covariances, everything. Can you use DAKOTA to quantify uncertainty in an ill-posed inverse problem, practical ill-posed inverse problem?
You want to quantify uncertainty in an ill-posed inverse problem. So, so an inverse problem we would characterize as a design in the presence of. So you want to calibrate your uncertainty model? Is that what you want to do based on data?
So a practical ill-posed inverse problem has this feature that depending on your slight variations in your data and additional parameters such as covariance,
right?
You can come up with a whole set of results.
Right.
With a big set of results.
Right. And so right now, if you were going to do a calibration for an uncertainty model and it's ill-posed, right now today we would leave the regularization approach up to you. You would formulate that in your quantity of interest that has been returned through DAKOTA in a loop like this for doing the inversion. I think that situation will be a fair amount different about a year from now. We're starting to put more focus on this class of methods. Right now we have a Bayesian inference capability which regularizes the problem through a prior. We also have a general nonlinear least squares under uncertainty, but without any specific regularization provided. You know, if you had adjoints and you wanted to do something like a penalization based on oscillatory behavior as evidenced through gradients, then a Tikhonov type. Am I answering your question? That there's a number of things that can be done. Right now, we have some of the general framework for doing calibration problems in the presence of uncertainty, but there's a lot more that we could do. Yeah.
Okay, thanks. I'll talk to you later.
Okay, I think we're going to stop the questions there.
Okay.
All right, I think we need to thank Michael again for that stimulating talk. And we're going to break.